Great to see so many here. A warm welcome. My name is Ralf von den Hoff. I'm directing the Freiburg Institute for Advanced Studies. Welcome to our 31st Staudinger Lecture here. The Staudinger Lectures are funded and hosted by the Freiburg Institute for Advanced Studies, as you possibly know, in order to bring Nobel Prize laureates from different disciplines to the University of Freiburg, to hear about their research and to get into discussion with them. Today it is Professor Anne Huillier who is here, and I'm delighted to welcome her very warmly here at Freiburg University. Welcome, Anne. Before I give the floor to our Vice Rector for Research and Innovation, Stefan Rensing, and to Giuseppe Sansone, currently fellow at FRIAS, and from the field Anne Huillier is representing, let me say some short words about FRIAS and what it is about. As you possibly know, and if not, it's time to do so, the Freiburg Institute for Advanced Studies is the International Research College of Freiburg University. FRIAS, which is the abbreviation, covers all disciplines. It invites outstanding scholars from Freiburg and from all over the world to apply for fellowships and for research stays at FRIAS here in Freiburg. Staying at FRIAS provides the opportunity to concentrate exclusively on a research project with excellent support within a stimulating working atmosphere, including unexpected and fruitful discussions beyond disciplinary limits with various other fellows. Giuseppe Sansone could tell you how much, for example, his research on attosecond impulses has enabled discussions with other fellows far away from his discipline about what time is, what the shortest period of time is, and all these questions. Beyond fellowships, FRIAS has much more to offer, funding research teams at our university, funding international cooperation of Freiburg University's research foci, funding conferences of early career researchers, and so on. I encourage and invite you to apply in one of our programs and calls, and individually, in a group, as a professor or as a postdoc. You will certainly not regret it. What FRIAS does includes also numerous public events. Among them, by these events, we give back some of the research done at FRIAS and at Freiburg University to you as the public audience. This is what the regular Staudinger Lecture is also about. Thus, with no further ado, I give the word to Stefan Rensing. Thanks again for coming. Thanks to the entire FRIAS team for organizing this again. And greatest thanks to Anne Huillier for joining us tonight. Merci beaucoup d'être ici et bienvenue à Freiburg.
Yeah, great to see so many of you here. Dear Anne Huillier, dear colleagues, dear ladies and gentlemen, I'm Stefan Rensing, Vice Rector for Research and Innovation, and on behalf of the university, its rector and its rectorate, I would like to welcome you here, as you heard, the 31st Staudinger Lecture that is taking place since its inception in 2008. This lecture really has been a cornerstone in our academic calendar, allowing really captivating insights into interesting research by, I would say, the most distinguished scholars worldwide, and, as Ralf was mentioning, a wonderful opportunity also to ask questions or engage in a discussion that you couldn't do otherwise. It's a particularly great honor for us to welcome you here today, Professor Anne Huillier. You're a leading figure in the field of attosecond physics, and since 2023, a Nobel Laureate in physics. She was awarded this honor together with Pierre Agostini and Ferenc Krauss for their groundbreaking experiments that actually have given us new tools to explore the world of electrons inside atoms, as we will hear about, and on the shortest time scales ever measured. I found it actually quite unimaginable what is 10 to the minus 18 seconds, and therefore I was asking before how far does the light travel in that time, and it's in the low nanometer range, so what you again couldn't perceive with the naked eye. So will be stunning to hear about that. Your work has fundamentally advanced our understanding of atomic and molecular processes, opening new avenues for research in physics, in chemistry, and beyond. We're deeply grateful that you accepted our invitation to join us here at FRIAS today, so thank you very much for being here today again. Also, I would like to express my gratitude to the FRIAS and to its director, Ralf Vondenhoff, for organizing this event. And I would also like to extend special greetings to our next speaker, Giuseppe Sansone, who is a professor for experimental physics here at the University of Freiburg, and also, as you heard, an internal senior fellow at FRIAS, and who has been collaborating with our guest today in many research projects, made the contact for this special event, and will us now tell more about Professor Huillier and introduce us to the fascinating world of attosecond physics. Thank you.
So thank you very much, Professor Rensing, and good afternoon, everyone. So as you already heard, my name is Giuseppe Sansone, and Professor for Experimental Physics here at the University of Freiburg. I work, now since 20 years in the field of attosecond science, so for me tonight it's really an incredible honor and an incredible pleasure, to introduce one of the founders of this field, Professor Huillier from the Lund University. So I would like to say really a few words about highlighting some of her main scientific achievements. And I would like to start from, let's say, from the very beginning, from her PhD thesis, which was done at the Research Center CA in Saclay, close to Paris. The topic of the PhD was the investigation of atoms under intense laser field, intense laser fields in the infrared spectral range. So, and the topic of this thesis eventually led, after a few years, at the end of the 80s, in 87, to one of the most important discoveries, for sure, in ultrafast optics, in ultrafast physics, I will say more in general of modern physics, which is the process of high-order harmonic generation. So, what Professor Huillier and a co-worker observed is that when an atom is irradiated with a strong near-infrared field, you can observe extreme ultraviolet radiation emerging out of this ensemble of atoms. So essentially, you can use these atoms to convert radiation in the near-infrared visible range up to the extreme ultraviolet, which has a much higher frequency. Nowadays, we use this process even to create soft X-ray and X-ray radiation. This was in the 87, and really for decades after these groundbreaking experiments, Professor Huillier was really the driving force, the main actor, both experimentally and also theoretically, in order to understand the main mechanism behind this process. So she was really totally devoted to understanding the physical mechanism behind this new discovery, and trying also to improve the characteristics of this process also for future application. Not only this, in her groundbreaking publication, she also highlighted the point that this radiation should be emitted in the form of attosecond bursts of light. And we already heard from the words of Professor Rensing, one attosecond, it's really something difficult to imagine. It's 10 to the minus 18 seconds, so it's a billions of a second. It's an extremely short pulse duration, and these are the shortest events that we can create nowadays. So, for these groundbreaking experiments and for all this work, she received in 2023 the Nobel Prize in Physics, shared with Pierre Agostini and Ferenckrauts. And in order also to understand the impact of this research, I would like to quote the official motivation of the Royal Swedish Academy for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. And in the motivation of the Royal Swedish Academy, we have also clearly stated which is the impact in science and future in technology of these pulses. They really finally give us the keys in order to observe the electrons, observe the electron in motion. So now, having attosecond pulses available, we are able to trigger, to monitor, and eventually to control the electronic dynamics in all states of matter. So this can be as simple as atoms and molecules, even though sometimes they are also not so simple, but can be also as complex as solid state materials. So this is the main motivation and the long impact of the work performed by Professor Huillier. I would also like to mention some other points which probably will not show up so clearly during the talk. The career of Professor Huillier, of course, is characterized by scientific excellence, by groundbreaking experiments, but also, what regards me personally, also for leadership and mentorship. And I would like to highlight 2 points. At the beginning of 2000, she coordinated the first European Marie Curie European network in our field. The Marie Curie network was called ATO, which grouped together all European laboratories working on the process of high-order harmonic generation. There were not so many at that time, and she started and coordinated this network, bringing all this expertise together. One of the first goals of this network was the first experimental demonstration of attosecond pulses, and this was really a success because already in 2001 there were 2 experimental groups reporting the temporal characterization of attosecond pulses. The second point I would like to mention is she has, of course, supervised countless PhD students, postdoc, and also colleagues in her career. And many of them, they've then stayed in academia, they've reached their own position, they've started their own research group, and now are those people who are even bringing further the field of ultrafast optic, ultrafast science. So they are bringing further the field, developing further attosecond physics, along the path that Professor Huillier started to designate in 1987. And so with this, I would like to ask you to join me in welcoming Professor Huillier as she takes us in the beautiful world of attosecond science.
Okay, well, thank you very much for the introduction. I'm very happy to be here. I think Giuseppe already told you what I'm going to tell you, how this field started a long time ago. So let me start by just what time scale are we talking about. 1 attosecond is a billion of billions of a second. It's very short. And if you follow this arrow, you see that there is the age of the universe is approximately 10 to 18 seconds. And here you have a few time scale, humanity with the Homo sapiens, astronomical times, the heartbeat. Then this is the time for mechanics, time for electronics. Here we come to the real microcosmos, time for atoms to move in molecules. And attosecond, this is the time scale for electrons to move in matter. In 1999, Ahmed Zeewal got the Nobel Prize in chemistry for the field of femtosecond chemistry, where for the first time they could really follow motion of atoms in molecules. So this is the outline of this talk. First I will talk about high-order harmonic generation, which was really the starting point for this research. Then I will talk about attosecond light pulses, and then how we use these pulses to study electron dynamics. So let me start with the discovery of the laser in 1960 by Theodor Meinmann. And the invention of the laser opened many, many fields of research. One of them is nonlinear optics. That started almost immediately after the invention of the laser, 1961. And here you have the experimental setup used by Peter Franken in 1961. You can look at the setup. You have a laser which is focused by a lens into a piece of quartz. The radiation is ionized by a prism, and then you have a detector. And on this detector, which at the time was a photographic plate, you could see 2 points, one due to the laser light and one due to the generation of the second harmonic of the laser. And here you have a representation of this process where the atoms absorb 2 photons from the laser and re-emit 1 photon at the double frequency. Another field that started after the invention of the laser is atoms in strong laser fields, very fundamental, and the study of multi-photon processes. Here you have a representation of a 2-photon excitation process, which was actually predicted theoretically by Maria Goeppert-Mayer in 1931. You can also ionize an atom by multi-photon absorption. These processes were studied by Russian scientists in particular in the 60s. In 1979, Pierre Agostini, so one of the Nobel laureates, observed the phenomenon of above threshold ionization, where an atom can absorb more photons than what is needed for the ionization. And you can observe these processes by looking at the energies of the electrons that are being emitted. And my own thesis work, which was in the 80s, beginning of the 80s, was to look at actually multiple ionization processes by multi-photon absorption. So at this time, we were convinced that in this interaction between laser light and atoms, we ionized atoms or molecules. We produced excited atoms, excited ions, and it would be really interesting to look at the fluorescence light that could be emitted from this excited species. So we set up an experiment. So this was in 1987. At that time, I was young researcher in the Commissariat Énergie Atomique in the group of Gérard Mainfray and Claude Manus. So we set up an experiment looking like this, actually similar to what I showed you at the beginning. You have a laser focused by a lens into not a piece of quartz, but now a gas of atoms. And you analyze the radiation, this time with a grating, and then you have a detector. What did we see? Well, we did not see fluorescent light. This is the beauty of experimental research. Sometimes you see things which are not expected, and this is really the most interesting. So what we saw was the phenomenon of high-order harmonic generation. Here you have one of the first spectra obtained in argon gas. You see peaks, and each peak corresponds to a harmonic of the laser field, which means that the frequency is equal to a multiple of the laser frequency. You can see that we only have odd orders, and this is due to the symmetry of the interaction. What was especially surprising in this result was that when you plot the intensities of this harmonic, you have this very characteristic behavior with decrease first. This is fine. But then you have this plateau behavior where all the harmonics are more or less the same intensity. And then you have a cutoff. And this was surprising because at the time we were thinking very much in terms of perturbation theory, where you expand the polarization induced in the medium by the laser in terms of series of powers of the electric field. And for such an expansion to be valid, you need the first term to be much larger than the third, to be much larger than the fifth, etc. Otherwise, the series just diverges. So this really meant that this was a non-perturbative phenomenon. If we look at where this radiation is on the electromagnetic spectrum, so which I represent here, going from radio waves to X-rays, and this is the visible part, very small. We start from the infrared. This is where our laser is, near infrared. And then you multiply by high frequency, and this takes you into a region of the spectrum which is called extreme ultraviolet. So it's below X-rays and above ultraviolet. It's radiation that is invisible to eye and is strongly absorbed by matter, so we need to work with vacuum equipment. Now, for those who are not physicists and who are already, we think this is very tough, you can, I'm sure you have heard about harmonics in other contexts and in music. And here is actually a harmonic spectrum obtained in when you play violin. You can compare with our harmonic spectrum. So the number of harmonics that you get when you play an instrument is really making the sound of instruments. And string instruments, for example, they have a lot of harmonics. In both cases, we have a strong interaction here between the string of a violin and the bow, and down between the atoms and the laser field. So strong interaction. Of course, here I'm talking about sound waves, acoustic waves, and now I'm talking about light waves, so very different type of wave, different frequencies, but analogy in the phenomenon. Now, to understand the phenomenon of high-order harmonic generation, you need to do both atomic physics, and I would like to say quantum mechanics. You know that 2025 is the International Year of Quantum. And this is described here. You need to describe what is happening to the electron, actually, in an atom when exposed to a strong laser field. This is described by a Schrödinger equation that you see here, which can be written as follows, with atomic potential here and laser atom interaction, written here in the dipole approximation. You can use a classical electric field, and again the dipole approximation. The difficulty of this problem is that this term here is almost comparable to the strength of the atomic potential. But you also need to do electromagnetism, which as a young researcher I find fascinating, this kind of double aspect of this phenomenon. You have a macroscopic medium with many atoms, and in order to see something, you need to have a certain phase matching condition to be achieved, which is represented here by this cartoon. The waves that are emitted by the atoms are in one direction, and they need to be in phase. This is phase matching, independently of where you create these small waves. So this is described actually by Maxwell equations of electromagnetism, and which can be simplified as a wave equation, as you see here, where you have a generated field due to the polarization in the medium. So in order to really understand the process, you have both this microscopic part, quantum mechanics, and this macroscopic aspect. And the first attempts to really understand and simulate high-order harmonic generation were done by a numerical solution of actually both equations that you see here, which was achieved at the end of the 80s, with relatively good success in reproducing the experimental data, but doesn't mean we understand the physics behind. Now I'm coming to the beginning of the 90s with huge progress in laser technology, with discoveries of a technique called chirpers amplification that led to Nobel Prize to Gerard Mourou and Donna Strickland, 2018. A new laser material called titanium sapphire, and also a new technique to generate short laser pulses called Kerr-Lens mode locking. And in several places in the world, particularly in Europe, in Lund, they are building new laser systems based on these three new technologies. And here you have a photograph of one of these lasers built in Lund by Sune Svanberg, Klaus-Göran Wallström. During that time, myself, still in Saclay in France, together with my first PhD student, Philippe Balcou, and then Pascal Salière, both of them are still in academia. We're building dedicated instrumentation to study these high-order harmonics. And it looks like this. It gives you a little bit of the scale. It's like this. What you see is vacuum chambers. You have pumps to get rid of air. The laser, you don't see it, is coming from a hole in the wall. And here you have basically the same thing that I mentioned already, gas jet, which is here, and then some optics to analyze the radiation that are in this chamber, and then a photon detector, which in this case is an electron multiplier, which is sitting here. So at that time, in Saclay, we were using a laser, which is called neodymium glass laser, with pulse duration of 1 picosecond, a horrible repetition rate of 1 shot per minute. So we were doing this experiment with this laser, and then I was invited by my Swedish colleagues to do experiment with their brand new laser with pulse duration 200 femtosecond, which is much better, and a repetition rate of 10 hertz. This is 10 shots, 10 laser shots per second. So you see the difference, enormous. So of course I said yes. And I sent this instrument to Lund, and my 2 PhD students and me, we drove to Lund and did experiments. And here is one of these experiments performed in helium gas. Here you see really many high-order harmonics up to the 93rd harmonic, with actually a beautiful plateau where all the harmonics have really the same intensity. Then a couple of years later, I was going to move to Lund, not for a laser, but for private reasons. You can guess. Okay, I'm now coming to the second part of this talk, attosecond light pulses. Actually, the idea that these high-order harmonics could produce attosecond light pulse came very early in the field, beginning of 90s. And the idea is presented here on this cartoon. So what I am showing is 3 different harmonics. So they have slightly different frequencies. So I'm showing the waves. Right? Now, if we assume that these harmonics are in phase at a certain time, which means that the maxima coincide. Because of the periodicity of the process, after half a laser period, the minima will coincide, and again, half a laser period, again the maxima will coincide, etc. This is called phase locking. We assume that the phase of the harmonic is locked. So if you sum now these three waves, you can do that in your head, you see that when they are in phase, then you will have constructive interferences. While when they are not in phase, here in the middle, you will have destructive interferences. So the light will be confined into short time intervals. If you represent the intensity of these pulses, you get something like this. You get a series, we call it a train of very short light pulse. And if you remember that half the laser cycle for our titanium sapphire laser is 1.3 femtosecond, so this distance here is 1.3 femtosecond. The duration of this pulse is a few hundred attosecond. And this is the first time one was talking about this time scale, attosecond. Just for information, atto is coming from the Danish language. I don't know if there are Danish people here. Aten in Danish means 18. So this is the origin of this term. Now, if you sum not only 3 harmonics, but 10 harmonics, you will get even shorter pulses. The reason why we can get short light pulses through this high-order harmonic generation is, first of all, that we have a rather high frequency, central frequency. You need to have a high frequency in order to have a short light period. So in order to have a short pulse with some certain number of periods in the pulse. And this is the case for the harmonics. We are in the extreme ultraviolet range of the spectrum. And of course, you need a broad bandwidth. This is an expression of Heisenberg principle. In order to have a short pulse, you need a broad bandwidth. And we have this broad bandwidth thanks to this broad range, this plateau of high-order harmonics. So the big question, which was really a question, was, are the harmonics phase-locked? And it's going to take us 14 years to actually be able to answer this question. In 1993, there was a huge breakthrough in the theoretical understanding of these processes with a model called the three-step model, which is presented here. And this was really a breakthrough by theorists. So let me describe to you this model. What is represented here is the atomic potential, which is distorted by the laser-atom interaction in one direction, so like this. Okay, normally it's like this, and the revolution symmetry, and because of the laser interaction, it's bent in one direction. On this side, we have a potential barrier, and an electron in the ground state can tunnel through this potential barrier, this beauty of quantum tunneling. Then the electron is outside the atom. It's driven by the laser field over a few nanometers. The laser field change of sign. Electron is driven back. And then there is a certain probability for the electron to recombine back to the ground state. And in this recombination process, you have emission of XUV radiation. So this was the kind of atomic physics description. Now I have a little analogy for the young, maybe not too young people here who are a little bit away from that. And this analogy is called The Adventure of an Electron in the Laser Field. It's in Swedish. Very easy, you replace C by K. Very easy. And you can represent this like this. We have a poor electron here in a prison. And that's good, because otherwise we would not exist. Okay? So a very strong electromagnetic force that is binding electrons to a nucleus. But then on the side, you have a roller coaster. This is the laser. So this electron would like to have fun. What does he do? You have to speak a little bit loudly, so I hear.
Break free.
Yeah. How?
To get tunnel.
Yes. You're very good. Sometimes I wait 5 minutes to get the right answer, but yes. This is called a tunnel ionization. Giuseppe, did you see that before or no? No? Then everything is fine, and the electron is very happy. This means acceleration in the laser field. Is going down and up, accelerated and decelerated in the laser field. Of course, this is the gravitation force, and I'm talking about the electromagnetic force, but the analogy actually is not too bad. So this story is unfortunately finishing very badly, and here is the end of the story. The electron is meeting on its trajectory the open prison, and it's falling. This is our recombination process, and screaming out its energy, which is the attosecond light pulse. End of the story. Okay. Going back to physics now. This process is repeated twice per laser period on each side of the atom. So what is represented here is kind of the motion of the electron going away and coming back, producing an attosecond pulse, and then again and again and again. So you have production of a train of attosecond pulses, and actually with a spin flip between consecutive pulses. And now you can ask, oh, but what is the relation of this with the high order harmonics? Well, if you sum this, if you go in the frequency domain from this is the time domain description of the phenomena. And now I go in the frequency domain, I do a Fourier transform, and I recover the spectrum of odd high order harmonics with this long plateau. So the explanation of the plateau is that, well, we produce short light pulse. Short light pulse means broad energy range. So actually we have explained this phenomenon in the time domain. Now, approximately at the same time, there was also a huge progress in the second part of the problem, phase matching. And let me explain it very simply. In order to achieve phase matching, which means that all the atoms send radiation that is being built up, you want the phase velocity of the fundamental field and the phase velocity of the harmonic field to be equal, so that both fields propagate at the same phase velocity. So you want the refractive index at the fundamental frequency and the harmonic frequency to be equal. So if we look at the variation of the refractive index over a large range of frequency, you see that in the visible region, visible or near infrared, the refractive index is larger than 1, while in this extreme ultraviolet region, it's less than 1. So it doesn't work, right? Fortunately, at the same time that we have this harmonic generation process, we have also a partial ionization of the medium. Some of the electrons that tunnel through, they are not coming back. They are really being ionized. So you create some free electrons in the medium. And these free electrons are going to change the refractive index at the fundamental frequency. You need to add a negative term, which is going to reduce the refractive index so that it becomes actually less than 1, so that you can have the same refractive indices for the fundamental and the harmonic frequency. And this happens for a degree of ionization in the medium that is typically a few %. So it's not very much. If you expose your medium to a very high intensity and ionize everything, you will not get high order harmonics. So you need a certain intensity in order to have this strong laser atom interaction, but not too much. Otherwise, you would not achieve phase matching. So it's a delicate balance here. It's a little bit more complicated than what I explained to you now. There is also focusing of the laser that affects this equation. But I don't want to go into detail. Now I'm coming to really very important experiments that were performed in 2001, which was the measurement of attosecond pulse. At that time, we thought that, yes, we could have attosecond pulse, but you never know. You really need to measure the pulse in order to be sure that, yes, this is what is happening. And let me present to you the experiment performed by Pierre Agostini, 2001. So he used a technique which is called the rabbit technique, which means reconstruction of attosecond beating by interference of 2-photon transition, and it's presented here. So he used a 2-photon transition, 2-photon ionization, which is represented here. You can ionize an atom by absorbing 2 photons. And you detect this by looking at the energies of the electron. Now, you create here a sideband due to absorption of harmonic Q plus a laser photon. This sideband can also be reached by absorbing the next harmonic and emitting a laser photon. This is stimulated emission of radiation. So now you have 2 quantum paths leading to the same final state. You need to add the amplitude of these 2 transitions. So you add the amplitude, which means that the result is going to depend on the phase difference between the 2 quantum paths. It's an interferometric measurement. So let's look at the phases of these 2 quantum paths. First, you have, this is due to this first path here, you have the phase of the harmonic, and then you have a contribution actually from the ionization process, which in the first place I'm going to neglect. So let's forget that. It's a smaller contribution. I come back to that in the third part of the talk. Then you have the phase of the next harmonic, and then you have a contribution, a phase due to the laser. The laser is delayed compared to the harmonic by a delay tau, so that you have a phase contribution here, omega tau. And here, this is an emission process, so it's minus omega tau. the signal that you will get, this sideband signal, will be an interference signal. So you will have a cosine term here, which depends on the difference of phases between the two quantum paths. So you have phi q plus omega tau, and then minus phi q plus 2 minus omega tau. So you get this phase difference here. So you see that you get an interference equation here that varies with the delay with a frequency of 2 omega. And through looking at this signal, you have access to the phase difference between consecutive harmonics. And this is exactly what I want to measure. I want to know whether I have phase locking between all of these harmonics. So he did this measurement, and from this phase measurement, as well as intensity measurement, he could reconstruct attosecond pulse train and measure for the first time pulses with duration 250 attosecond. In parallel to this, you had again progress in laser technology with really progress in making very, very short light pulses. Using in particular the hollow fiber compression technique that you see here was developed in the group of Mauro Nisoli in Milan. This is a photo of this hollow fiber compression technique, and also realization of the importance of the carrier envelope phase of the electric field of a laser. And this carrier envelope phase is simply the difference between the maximum of the electric field and the maximum of the envelope. Using these techniques, Ferencross and his group, at that time in Vienna, managed to generate a single attosecond pulse and then to measure it. They used actually a technique a little bit similar to the technique developed by Pierre Agostini, not really interferometry, but cross-correlation. And this technique is called streaking camera. Very simply, you ionized an atom by absorption of the attosecond pulse in presence of the laser pulse, and the electron can get a momentum from the ionization plus a momentum from the laser, and this depends on when the ionization takes place relative to the laser period. So this leads to this beautiful streaking trace that you see here, and that allows them to determine the pulse duration, in this case 250 attosecond. So now I'm coming to the third part of this talk, which is study of electron dynamics. So I'm going to be a little bit tougher here. Okay, so we'll see how many can follow. It's just a little warning. So let me start very simply. What do? We look at the simplest possible actually process, which is the photoionization of atoms. And it's the photoelectric effect that was discovered by Hertz, 1887, and explained by Albert Einstein, 1905. Now, Albert Einstein used the newly concept of light quantum or photon to explain the photoelectric effect. But I would guess that, I don't know, I mean, he was so smart, so I don't know, but I would think that he was thinking of the photoelectron as a particle, right? A particle being emitted from the atom and going to the detector. You can detect its energy or its momentum. It's a particle. But we know that it is also a wave. And actually, what does it mean to follow the electron dynamics? It means to characterize the electron as a wave, characterize the wave properties of this electron. And this is what we are doing. How do we do that? Well, actually, very similar to what I already explained, what Agostini did using this rabbit method, using interferometry. So what I'm representing here is an electron wave packet, broadband. So this is the blue thing. It's an electron wave packet, which is broadband in energy, which is being excited by absorption of a train of attosecond pulse, which means harmonics, as is represented here. And we're going to determine the phase property of this wave packet by interferometry. Same technique. So we are going to try to measure the phase variation of the wave packet across its spectrum. I already said that the phase here depends on the harmonic phase and a phase due to ionization. So now I'm changing perspective. The interesting phase here is this atomic phase. How do I get rid of the first one? I'll tell you later. Okay, just forget it for a moment. So we are measuring this phase. Actually, we are measuring the phase. We do not measure any absolute phase. Okay, we measure phase variation. So we measure phase variation across the spectrum here, which means we measure the derivative of the spectral phase. This is a delay, a group delay in optics. So what we are trying to measure is the delay, the group delay of this electron wave packet as it's propagates in the potential. And here is kind of a cartoon illustrating what I just said. We really try to measure the delay, how long it takes for the electron to propagate in the potential. What is the delay as it propagates? A little bit similar to a delay of a light pulse as it propagates into a material. This is actually a concept that was already introduced by Eugen Wigner in 1955, the group delay derivative of the scattering phase. So you see that here I have tau at, and here I have tau w. It's not the same notations. That means that in reality, what we are able to measure through this technique is this Wigner delay plus a small correction, which is due to the measurement process, which also involves a laser field, which also involves this interaction here, which is needed for the interferometric measurement. How do we do this measurement? This is a picture of the experimental setup. If you are interested, you can. There are many such setups in Giuseppe's lab, so you can ask him to show that. Basically, what you have is an optical interferometer. In this case, it's a Mach-Zehnder interferometer. You split your laser into two. In one arm, you generate harmonics or attosecond pulse train, and then you filter out the fundamental field here so that you have only the attosecond pulse. And then in the other arm, you have a fraction of the laser which is delayed very accurately relative to the attosecond pulse. So you produce the combination of laser and attosecond pulse with a variable delay. And then you do electron spectroscopy using, for example, a magnetic battle electron spectrometer or another type of electron spectrometer, and you put some gas here and you measure the electrons. What do you see? Here's a picture of what is called a rabbit spectrograms. So it's an electron spectrum as a function of delay. So what you see here are peaks. So you have main bands due to absorption of the harmonics and emission of electrons, and sidebands, which are due to absorption of harmonics plus one laser photons. And you see that these sidebands oscillate very nicely. And the period of the oscillation is this half laser period using titanium sapphire laser 1.3 femtosecond. Now I come to the question, how do we get rid of this contribution from the harmonic phases, from the excitation light? Well, there are several ways to do that. I'm just going to present one way to do it, which is, well, okay, we cannot exactly measure this delay because of the contribution from the light, but you can measure differences in delay. For example, if you measure photoionization in neon at the same time in the 2s and the 2p shell, you are going to be able to measure the difference in delays. So this is an example here where you measure the sideband here, 42. This is from 2s ionization, and the same sideband, so involving the same excitation light for 2p. And then you compare the oscillation. For 2s, we have this phase offset depends on the atomic delay 2s plus the group delay of the attosecond pulse. And here you have the same for the 2p, and you can simply make the difference. So if I represent what we are doing on a clock, so 1 hour on our clock is 1,300 attosecond. This is half the laser period. And what we are doing in this measurement is we are able to measure very accurately the position of two arrows on this clock. However, we don't know where these two arrows are. It's really a difference measurement, but difference between these two, very accurate. What do we get? I'm going to show you two results with different conclusions. This is neon, comparison between 2s and 2p ionization over a rather broad spectral range. Extremely good agreement between theory and experiment. Extremely good temporal accuracy. I hope that you agree with me. The precision that we had in this measurement is like 20 attosecond. Is really incredibly good. It's the best measurement we ever did, I think. Let me show you another result. So we are very happy, very good agreement. Let's do the same in argon, 3s and 3p. First of all, look at the time scale. Here we have from minus 400 to plus 400 attosecond. The points are experiments actually performed both in Lund and in Saclay. This is actually a problem we have been working on 15 years, still not finished. So just to tell you that these are not very easy experiments or theory. And this is the theoretical calculation using a technique called random phase approximation with exchange. Well, what do you see? In this region, we have a very good agreement. Here we have a complete disagreement, and this is a huge difference. What is the difference between the two? Well, in the first case, in neon, the Wigner delay is actually almost zero, which means what we measure is actually this correction due to the measurement. And we know how to calculate it very well. So this is why we have very good agreement. So maybe not much physics in this measurement. At the same time, it was a very important measurement to really confirm that we knew what we were doing in this type of measurement. Now, in the other case, is the opposite situation. This correction is actually negligible. And we have what we're looking at is really this Wigner delay. And what is fascinating in this comparison is that, first of all, if you use the same theoretical technique and you compare with the cross-section in 3S and 3P, in 3S especially, you have perfect agreement. So cross-section works, no problem. But now here we are measuring phases, delay, and we see a huge disagreement. This is for 3S ionization. And the physics behind is really very different, because according to theory, in this region here around 42 electron volt, the electron is trapped in the potential. I'm putting physics behind these curves. It's trapped during almost 400 attoseconds. Whereas according to the experiment, it's just the contrary. The electron is pushed. It's moving away very fast. It's getting some kind of advance. Which one is right? Experiment, of course, yes. This is to be continued. So let me finish this talk. So, no, seriously, this is where we are. I think now there are more experiments which confirm the strong negative delay, and it seems that theorists are modifying their theory, including more correlation, doubly excited states, in order to get a negative delay instead of positive delay. The message maybe is that this type of new measurements are really complementary from traditional measurements with synchrotron radiation, leading to cross-section measurement. Here we are measuring something else that is really important to have the complete physics of this interaction. Let me conclude by discussing another case where we are again looking at electron dynamics, but now we are creating a little bit smaller wave packet by absorbing one harmonic photon here. And we would like to characterize this wave packet. And this wave packet is created in the vicinity of a discrete state here. So it's a beautiful example of quantum interference, where an atom can be ionized either directly or by excitation followed by autoionization. This has been particularly described theoretically by Hugo Fano in the 1961. So can we measure again the wave properties of this wave packet? Yes, we can, using the same technique, using interferometry. What do we get? So we do that in helium. We have done that also in argon, but in helium, for the 2s2p doubly excited state that you have here, and then using harmonics 37, 39, and we look at sideband 38 to get this phase information. And this is the measurement showing the amplitude as a function of energy. So it's a beautiful interference effect that has been studied with much higher spectral resolution before. But now what is new is that we can now measure the phase variation, which here is the phi, it's a pi phase jam. So now if we know the amplitude and the phase, spectral amplitude and the phase, we can go into the temporal domain and by Fourier transform and really follow the dynamics of this ionization process. We can even do better, which is to make a time frequency representation of this photoionization process. And this is what is shown here. It's a Wigner distribution, which showed you the physics of this photoionization process in the time frequency domain. with first direct photoionization, which happens first. This is a broad energy region over a short time. And then you have strong interference in this region where both interfere destructively. And then you have mostly the photoexcitation process followed by autoionization, which is narrower in spectral range and longer in time. Now, the next question we ask is, can we always do that? Measure, we think of this electron wave packet a little bit like a light wave, but it's not really, it's not really a light wave. So the question is, can we always do that? Do we always have a coherent wave packet? The answer is no. And a few years ago, we thought, can we really measure the quantum state of a photoelectron, characterize the density matrix of the photoelectron? And we developed a technique to try to measure the density matrix of a photoelectron. So again, here I'm creating a wave packet, and I'm trying to probe this wave packet to measure its properties using this time a bichromatic probe field with two frequencies, omega 1 and omega 2. Same idea, I'm doing interferometry with absorption of one XUV photon plus the red photons, or another XUV photons plus the orange photon, leading to the same final state. And the interferometric signal looks like this, where it's not 2 omega as before, up and down. It's like this. It depends on delta omega, which is the frequency differences between omega 1 and omega 2. And the quality of this interference signal is going to depend on whether there is a good phase relationship between the two different frequencies of this wave packet. So it's going to depend on the coherences of the wave packet. So thanks to this technique, we can actually measure the density matrix of a photoelectron. These are measurements performed in helium. So the diagonal is in this direction. And for a given pair of omega 1, omega 2, you have access to one point outside the diagonal. So by measuring the spectrum, you get subdiagonal, and then we vary the frequency differences, and we can measure a few subdiagonals. And there is, of course, the symmetry relative to the diagonal. We can make a fit of these measurements, and this is what we obtain. Very nice, very round. This is pure state in the case of helium. We do the same measurement now in argon. And this is what we get. It's not round, it's elongated, which means that we lose coherences here on the side, so it's a mixed state. So why do we have a mixed state in argon and not in helium? Anyone wants to guess? I'm looking at very good atomic physicists here that should know the answer. But anyway. The reason is called spin-orbit interaction and spin-orbit splitting. The threshold here is split into two states. So the ion can be left in different states. And so when you ionize argon, you actually create an entangled state because you don't know if the ion is going to be left in the 1/2 state or the 3/2 state if you don't measure it. And since we are not looking at ion, degree of freedom, we're just looking at the photoelectron, we trace over the degree of freedom of the ion, we lose information and we obtained a mixed state. So this is, I'm going to conclude on this. This is one of the really, where is the research on this on this problem nowadays. So to conclude, the attosecond science is a little bit going into many, many directions. Now I have discussed atomic spectroscopy. I think one of the big challenge of our field of research is to look at this electron dynamics, not in simple atoms as we are doing, but in molecules or in condensed matter. There are also some applications in industry, and this kind of interesting aspect now towards quantum optics, and Giuseppe is now coordinating a network on these aspects. There are also attosecond sources, not only by high-order harmonic generation, but also by free electron lasers, giving attosecond pulses at much higher photon energy in the X-ray range and also higher energy per pulse, so opening really towards nonlinear optics with attosecond pulses. So to conclude, I would like to thank you very much. Thank my research group that you see here. These are the senior people in this group. Also theoretical support from many people, and especially Markus Dahlström and Eva Lindroth. And I would like to thank Giuseppe for very nice collaboration during many, many years, and his group, and also nice collaboration on this last quantum aspects with the group of Andreas Büchleitner. And you maybe recognize here Christoph Dittel, who just spent 1 year in Lund, and before he was at FRIAS. And let me also thank some organization financing this research. Thank you very much.